All right. So hello and welcome to Algorithms Live. And this week I'll be going over this technique for tree traversal trickery. It's really not one technique. I'm going to go over some properties of preorder postorder numbers, and I think some surprising tricks for solving problems on trees that this pattern comes up every so often. I also want to explain some relationship between trees and preorder postorder numbers and parenthetical sequences. I think that's kind of interesting. So that's basically the focus of today. We're going to work one problem. I'm going to code it live. And depending on how much time we have, I want to play around with coding it a different way. There's another technique I want to show. So there's more than one way to solve this problem. So I want to go through both of them. But what we'll do is I'll dive right in. All right, so let's start off with something simple. The main idea here is we're given some kind of a tree. And then maybe something on this other side. And here's the problem. So we have a tree, and we're going to put values at nodes. So maybe I'll put a 1 here, a 3 here, an 8 here, 7 here, 2 here, 4 here, 5 here, 6 here, 7, something like that. So what we'd like to do is we'd like to be able to update values. So maybe I have this 6 here. I want to change that to a 2. So it's a tree position change. And then I'd like to also do something where I can query a whole subtree. So query a whole subtree sum. So the idea is if I pick this node right here, well, now I take everything. And that's the idea, is I basically get the sum of 1 plus 2 plus 3 plus 8 plus 7. And that would be my answer. So we could do this fairly naively. One thing you could do is just update the nodes, and then every time you get a query, do a DFS down that subtree and figure out what the query is for the answer. The problem is that's O of n per query. But at least the updates are fast. I could update a single node, and that's O of 1. So I'd like to do something about that O of n. Another thing I could do, just thinking about this problem a bit differently, is I could store for every single tree position, I could store the subtree sum additionally. So maybe for this node, I'd also store that it sums to 18 for its subtree. And the trick here is now my queries get fast. So my queries are O of 1 per query. But now I have to update every time I change a node's value, I have to update all its ancestors in the tree. So I just follow the chain of parents up. So you can actually do that with binary lifting if you want. That is one valid approach to doing that update. I think you might have some complications. You could also do something with heavy light decomposition to do those updates quickly. That's pretty heavy as well. So I'm going to show you guys a simple way of solving this subproblem just by knowing how preorder and postorder numbers work. Okay, but that's our motivation here is we want to solve this subproblem very quickly if we can. So I'll draw out another tree. So there's my tree. So what I'm going to do is I'm just going to do a DFS. So if you haven't seen preorder and postorder numbers before, it looks something like this. You keep a counter, running counter going down the tree. And every time you enter a node, this is the first time you hit this node, you may mark the counter at that time. So it's like you've got a stopwatch, you stop the counter. And then you move on to the next node in the traversal. And then the last time you touch a node, you also hit the stopwatch again, and that's your postorder number. So I'll go down my tree. And you can see I'm just updating these preorder and postorder numbers. 2 and then so 9, 10, 11, 12, 13, 14, 15, and 16. Did I mess up horribly? Yes, I did. Or maybe not. Let's take a quick look. 4, 5, 6, 7. No, these look good to me. All right. So let's take a look at what this is getting me. So I end up making these preorder and postorder numbers. Let's look at a node I, and maybe it's got a path down and there's some node J. We can look at the preorder and postorder numbers of these nodes. We have AI and BI. And we have AJ and BJ. And so I can get some range. Maybe this is I's range from A to B, and this is J's range from A to B. And what you'll end up having between I and J is an interval where this interval is completely contained within I's interval. So you get this nested interval structure. So subtrees are contained in intervals, and they're nested intervals. So let's say I draw out a tree like this. We get this nested interval structure that looks something like from here to here, here to here, here to here. And those would correspond to the preorder numbers. So it'd go 1, 2, 3, 4, 5, 6. And those are my preorder numbers. So you can look at them 1, 2, 3, 4, 5, and 6. Okay, so let's take another look at this. So this is also another lens you can view preorder and postorder numbers with is balanced parenthetical sequences. So here's a transformation. Take a look at this. So if I take the preorder number, whenever the preorder number occurs, what I'll do is I'll say that's an open parenthesis. And every time a postorder number occurs, I'm going to say that's a closed parenthesis. And so now if I take this tree like this one up here, and if I'm doing my DFS down, I could end up having 1, 2, 3, 4 open parentheses because the first 4 preorder numbers are the first 4 numbers are preorder numbers. But then I get to that 4, 5, so I get a closed parenthesis, open on 6, close on 7, close on 8, open on 9, close on 10, 11 is closed, 12, and then I can do 13, 14, 15, and then 16. And so this is the parenthetical statement that corresponds to the traversal of this tree. So you can always go from one to the other and have this work. Here for the smaller tree, you can kind of see how this ends up pairing up nicely to the intervals. You can end up getting open and closed in this manner. So typically what you'll do to make problems easier, you can call this like a tree linearization, is compute the preorder postorder numbers and take advantage of the fact that they're self-contained intervals in some bigger interval like this. Okay, so let's get back to our original problem. The original problem was storing these nodes in the tree and then querying for a subtree, like what's the sum of values in some subtree. Well, I could store all the values in the preorder number locations. So I could think of, instead of thinking of this as a tree, I could think of this as an array from 1 to 16. And then every time there's a preorder location, so let's do this smaller tree. So here's where I'm storing where the root node is. Here's where I'm storing where the left child is. Here's where I'm storing what the right child is. I'm going to store those values there. And if I want to do a query, so if I want to do a query on the root, well, now I've got a range that I could query, and I'll capture all the preorder numbers that are contained in my subtree. So query subtree a range sum. So now we just need a data structure that can do point updates. So update a single location in an array and then do range sums. And so if you remember episode 0, we can just use a Fenwick tree for this. Very handy data structure. And so that's going to support login updates and login queries. So that's all you do. And so now we have a fairly simple to code but efficient solution to this problem. All right. But that's not all preorder and postorder numbers can do. So that's our very first problem we're going to do tonight, was just this one. And if you have any questions for anyone watching live, just drop them in the chat, and then I'll answer them a bit later. But we'll move on to this problem called family fortune. All right. So what I have here is I have a tree. Right. So I end up having 1,000. I have 8. I have 11, 12. I have 4. I have 6. I have 1. And so you're given a k value in this problem. So let's say k is 3. And so we have to select exactly k nodes, but no node can be an ancestor of another node. So if I picked this node and then maybe I want to pick 100, well, these two are in conflict right now. So that's a problem. So I can't pick them both. So I believe for k equals 3, I could pick these 3 nodes, and I want the selection of nodes that maximizes the sum. So we want max total sum and exactly k nodes. So somewhat strange property of this is 1,000, or this 100 right here. If k equals 3, I can't take it, because my answer has to be exactly k nodes. So you can have a really expensive thing and not be able to take it that's more than your answer even. So a strange consequence of this problem. Let's talk bounds. Bounds here are pretty big. So the number of nodes in this tree can be up to 10 to the 5th, and k can be up to 1,000. So we're already looking at some pretty big bounds. This k is fairly suspicious. Okay, so typically when you're exposed to a tree problem like this, particularly problems that look like this looks like some sort of knapsack problem. So the first idea that comes to mind is some sort of tree DP. So we could do a sort of tree DP. And I just want to walk through this a little bit of how you attack this with tree DP, and why this problem ends up being a bit harder if you start looking at it through that lens. So imagine I'm at the root node. What I'm going to do is for every single node, I'll make a function f of I. This is the node I'm currently at. And what I want to do is I want to return a DP table that from 0 to k inclusive, what's the value I could get for taking exactly k nodes in a subtree. So if I'm at some node I, I'd like to just know for this entire subtree rooted at I, if I am allowed to take exactly 3 nodes, how many, what's the reward I can get if I can take exactly 4 nodes? And of course, I put in negative infinity or something ridiculous if I can't take any of those nodes. All right, so we end up having this problem of, given a tree, and it's going to have some subtrees where this is already computed, can I combine these subtrees together and get the maximum sum possible? So I'm going to have one of these tables computed for every single one of these subtrees, and I end up having to combine them together. So it turns into a sort of knapsack DP, right? So I've got my table over here. This is for the first child, and it's all its values from 0 to k. And then I need to allocate, maybe this is my DP so far. I end up getting some costs from 0 to k as well. And my transition for saying, okay, if I combine these two subtrees together, what's my minimum cost? Well, I need to allocate some amount of k over here and some amount of k over here to get position k plus 1, or k plus k1 plus k2 in my next table that I'm considering. So you can do this with a double for loop. You could just loop over all values of k that you want to get to big K, and then just split them up. So you allocate some to K1, whatever remains to K2. And the main thing I want to point out here is this intermediate piece is K squared. So we could do this subtree thing going up for every single node. But the problem is my runtime, I'm going to say this is hard to prevent some DP that's O of n times k squared. And I might actually code the n times k squared a bit later in the show. So but you can already see that's tricky. But apparently this is possible. And so that's what I want to do at the end of the show, is play around with seeing how this is possible, see if I get a aha moment on how to solve this. Because this is actually the intended judge solution. So that's the first idea. When you look at this problem, you start thinking down this path. But I want to show you how you can use preorder and postorder numbers to completely subvert this idea and just do something entirely different. So I'm going to use tree linearization and look at it that way. So just the idea of preorder and postorder numbers. Okay, so this was idea 1. And idea 1 is complicated, is all I'm going to say about idea 1. So let's try idea 2, which is using this idea of preorder and postorder numbers. Okay, so I'm at node I. What I want to do is, if I take node I don't want to consider anything in the subtree. We want to kill the entire subtree off. If I don't take node I can start going down the subtree. So here's the rough idea. I want to consider going into the first node of the subtree. If I end up taking that node, and then consider all the subtrees here. So this is option 1, enter subtree. And then option 2 is go somewhere else. Okay. So if I'm considering my nodes in preorder traversal order, one really nice thing about the preorder traversal order is all the subnodes in a given subtree are their preorder numbers are all clumped together. So let's say this is node I. Every preorder number in I subtree is right here. And then as soon as you leave I subtree, you get a little pocket where you could jump over the entire subtree. You can draw any preorder traversal of a tree out, and you'll actually notice it has this property, which is nice. So let's do this on the sample. And I'm just going to show the preorder numbers first, and then we'll write in some other information. So I'll write in 1, 2, 3, 4. So I'm not even doing postorder numbers. I'm only writing in preorder numbers. 5, 6, 7. Right? So that's what I can do. And what I want to do, notice that if I pick this subtree, well, then 2 and 3 are contiguous. And then 5 is the next preorder number that I care about after I've explored this entire subtree. Or I could pick this subtree, then notice these are all lumped together. And you can draw much more complicated, larger examples and figure out that they all they're all clumped together like this in terms of preorder numbers. And this makes sense because I basically, for traversal, I go down this branch, explore this entire subtree before coming back up. And that's why my preorder numbers are all clustered together like that. Okay, so when I leave a node, what I could do is I could say, what's the next preorder number when I'm leaving? So if I'm at 3, my next preorder number was 4. If I'm at 4, my next preorder number was 5. If I'm at this node, my current counter when I'm leaving the node, its next preorder number is 5. So in other words, if I just finished processing this node and I want to see the next preorder number that's not in its subtree, that's this node right here. And I can just build this entire table like this. So here's 6. Its next preorder number is 7. 7's next preorder number is 8. 5's next preorder number is 8. And then 1, you either jump off the end of the tree like that. Okay. So I can do is I can build a sort of table based off of the preorder numbers. So I'll do here is I'll make a table of preorder numbers. So this is 1, 2, 3, 4, 5, 6, 7. We make it a bit larger. All right. So I'll put in the costs for every single preorder number. And this one's X'd out because it's not actually a node. It just jumps off the end of the table. So one of the things you'll notice here is I can immediately jump to my next preorder number. So I'm just going to be considering them in a sequence. And that will take care of option 1. Is option 1 basically jumps to the next candidate node without consequence. And if I only take options 1s, which are just jumping to the next node like this in terms of going through it, then I'll go through everything and not take a single one. But if I want to pay the cost for a node, if I want to pick a node in the subtree and not consider anything in its subtree, then I need to do the jump. And my jump is basically going to this number right here, this postorder type number, even though it's not a separate number. It's the next preorder number that's not in my subtree. So I can actually compute all these things. So this one goes there. This one goes there. 4 goes to 5, something like that. Let's see, 5 goes all the way to 8. 6 goes to 7. Yeah, and I think that's all the jumps. So in other words, when I take something, it's kind of like a game of chutes and ladders, or almost like a skip list, but without a bunch of extra links. If I decide to take this node here, all I do is I just jump further in my state than I would otherwise, because I'm just jumping over everything that's in my subtree. And then if I don't take that node, then I just stay where I currently am. So what we get is a sort of knapsack style DP. So our state is what node I'm at I and how much k I've taken. That's going to be my state. And there are only 2 transitions here. So the first one is take the reward. And that means you have to take the jump. Or don't take the reward. And I can just go to the next preorder number. And that's sort of how my knapsack DP works. And you'll notice for this solution that this ends up being n times k. Because my transitions, there's only 2 transitions, and this is just an n times k DP. So that's my idea for how you solve this problem. I'm going to show you how to code this. And then what I want to do is I want to jump back to the other solution type and see if we can figure out how to make it n times k as well. Let's start with this. Okay. Yikes. Forgot that I coded most of this. Let's get rid of all this. Ah. I'll keep some of it around. Just playing around, making sure that the data was correct. Didn't have Windows line endings and stuff. Okay. So what I'm going to do here is I read in N and K. That's my graph. The graph's kind of in a weird state, so I'll just do my usual. So that's okay. So the graph's just given to you in this weird way where you just read in the parent. And of course, it's one indexed. So let's get around that. There's kind of two cases. If it's -1, it's the root. So I'm actually going to keep track of where my root is. That's going to be I. So root is -1 initially. That way it crashes if there's no root. Otherwise, what I'll do is I'll just add myself to my parent. Okay, so that's that. Oh, I also have to store some weight information. So this is the reward for taking a node. It's going to be N. Should also mention that there's another problem in the blog that's very similar to this, but it's a bit different. So it uses the same, it can be solved with the same trick. So if you want to practice this technique after the fact, you can go look in the blog and go solve the problem knapsack, which instead of not taking ancestors, you're required to take all your ancestors if you take something. So talk about that twist. Think about that twist yourself. All right, so what I need to do here is I need to make preorder numbers. What I'm going to do is I'm going to save the inverse of the preorder number, and I'll talk about why I do that in a second. And also store this jump array as to where I'm jumping after the fact for my preorder number. If I'm doing a preorder number thing, I'm going to need a counter, so I'm going to store that information as well. Okay, so this is what I mean by preorder side. You basically save the preorder number on this side of the DFS if it's a preorder, and you save it on this side as a post order. So I'm going to make inverse P of whatever my preorder number is, be I. So that way I know the thing with the ith preorder number, what node was it? Of course, I need to save what pre is, so I'll do counter ++. So initially counter is 0, it's just going to be incrementing. I know in the examples I was drawing it out starting at 1, but that's not a big deal. Jump. So what I'm going to do is I'm going to say whatever this preorder number is, jump is what's the next preorder number after this preorder number. And the reason I'm doing all this finagling, getting the inverse of the preorder number, is I don't want to sort my weights again. Just makes life easier for me. I don't have to go write a sort or make a class or anything like that. But you could do it that way if you prefer. This way just seems to be a bit easier. All right. So let's get some extra stuff. So I'll make my counter 0 initially. These tables both have to be size n. So there's my jump table. Now I can call DFS on the root. That gets me my preorder numbers. So I should have a way of jumping to the next subtree that I'm considering and jump to the next preorder number. Great. So now I can do my DP. I'm actually going to run this one iteratively and say I'm on I've taken k things so far. That's my current state. And I want to get to the next value of k. So I'll do this space-saving style DP. So this is my current level. I've taken k number of things. And next is going to be k plus 1 number of things. So it's just a standard iterative DP. So what I want my base case to be is I want a really small negative infinity type value for all my k's because I have to take exactly k. And that's why I'm saving that. But if I take 0 things, then my cost is 0. This will be an easy way to detect that. OK. So now I'm just going to loop through all possible k values, and I'll update the ith row of my DP table. So here's how this works. I'm just going to loop through all the nodes. And so this isn't the I in the problem. This is the ith preorder number. Keep that in mind. So I'm on. So my current state is ik. So I is the ith node of the preorder number. And my k is taken k nodes so far. So I do a kind of like build out style dynamic programming. You've probably seen me do this in earlier episodes. I think of dynamic programming in terms of BFS in my head. I think of what's my base case. That's where I'm starting in terms of my BFS. And then I think of what states can I reach. So if I'm already at the ith node, I've already taken I nodes so far. The 2 states I can reach after that are going to the next node, I plus 1. And so I plus 1 means I didn't take this node. So I don't get the reward. So I'll take whatever my current DP is, because my k doesn't change, of I plus 1 ends up equaling the maximum of what's currently there, or I like that. So really what I'm doing is that this right here is a transition from I comma k to I plus 1 comma k. And so I'm just using cur to represent the kth row of my DP table. Then I also have to do a transition from ik to taking this jump. So I need to do wherever the jump of I leads. And then I've taken an extra node in terms of the scoring. So I'll do next of I plus 1 equals the max of whatever next is at, or whatever I'm currently at. And now I have to pay my reward. And if you remember, my reward isn't at node I. It's actually what it was in the input, because this is the preorder number. So that's where I use my inverse preorder number table to figure out exactly what I'm paying. Should probably fill in the next piece of my array. So integer dot min value. So I don't want the next row of the DP table to have anything in it. OK. And so now I just copy over next, because that's the next row of my DP. So I've just calculated row k of my from row k of my DP table, which is initially k equals 0, to row k plus 1. So now k plus 1 is going to be the next iteration of this for loop. So I just copy over the entire array. I need to take n with me as well in terms of my jump. So I'll just take next of I, or cur of I, is whatever I just calculated. That's my DP table. And so now I need to save my results. So it doesn't matter what node I end at. I could end at any of the nodes as long as I've taken exactly k things. That's what I care about, and that's what this DP will hold. And so I can just print out the result. See if I can get the samples right. Yikes. Super wrong. I have a bug somewhere. Let's see if I can fix this real quick. Yeah, maybe I'll print out the pre-order and post-order numbers for good measure. Yeah, those look good. So that does not look wrong to me. So then something in this current next. Oh, I didn't take the jump. Right. So this should be transitioning to jump of I, not I plus 1. That was a big mistake. Yeah. I wrote it right in the comments. Okay, so basically what I want to do is, this is the jump state of actually taking it. Taking the reward and then ignoring the subtree. And so those values look right. Those are the samples. So what I'll do here is I'll just run on their official data. That was pretty fast. This is an old. Oh, time's not available. I need to put bash on here. The bash shell for Windows. So you'll notice that these are all of the test cases are in one file. This is an old ICPC problem, so it's kind of unfortunate that we have to deal with that, but okay, and I got it correct. So that's one way we can approach this problem H. And we actually have to figure out, you just turn it into this knapsack problem. So I want to do for the remainder of the episode, because it looks like we still have tons of time, is I want to go back to idea 1. And I want to just talk about this problem of returning things about subtrees and not using the preorder traversal information at all. See if I can end up arriving at some kind of conclusion on how to do this, because I've never actually solved it that way before. And I might get stuck. But I think it'll be fun. I think it's kind of that whole messy problem solving thing I just kind of want to demonstrate. Okay, so this is one solution to the problem. So what I'll do is I'll just delete all my nice code that I just wrote, but keep around the boilerplate. I don't need anything involving preorder numbers. Still need to read in my graph. And I don't need any of that. So let's code the naive n times k squared solution. That'll be a good starting place. And I'll just show you how to do that. So what I'd like to do is I'd like to make a function called go. And this is the function I was talking about, where I have node I. I've just processed node I. I want to know a table from 0 to k in size. What's the max I need to take to get that amount? What's the maximum reward I can have if I end up taking exactly k things in that subtree? So that's what I'm going to compute here. Yeah. And I'll keep k around like that. Okay. So what I'll do is I'll make my DP size exactly k plus 1. I'll do is I'll fill this with integer.min value. But there are some special cases. If I take exactly 0 things, then my answer is 0. And if I take exactly one thing, then I can just get the reward for node I. So I'll move my reward function, our reward array out to here so I can use it. Okay. So now I just loop through all the subtrees and I'm solving the subtrees. Basically what I'm saying here is calculate the DP table for this subtree. And now I have to I've used exactly k things down this subtree right here. So I need to update my DP table so far. I'm always going to use at least one thing from my table or else it's not useful. Here's the idea with this DP. I'm basically saying, I know here are all the different ways I can take exactly k things in the subtree. Can I use some amount of these k's down here? And maybe I'll make this 0. Can I use some amount of these k's down here in the subtree to update my DP at I and end up calculating, update what my DP value is here? I'm going to assign some amount to my subtree. I'll call that K1. And I'll assign it always at least one thing. And maybe I'll put in a small optimization. So if DP2 of K1 is, I'll break. Otherwise, what I can do is I can update my DP. So DP of K equals math.max of what's already there. And DP2 of K1 plus DP of K2. So let's calculate K2. K2 is just K minus K1. I'm basically splitting up the allocation that I want to have for this DP table. And I can just return DP. It's kind of recursive. I basically, I'm doing a sequence like n squared style space saving DP here. But then when I'm done calculating that for node I return it so that the next one can do an n squared kind of sequence DP for that node. So my answer for this problem is just going to be, let's call this the resulting DP. So I'll just do a search for my root, and I'll just print out whatever the result is for exactly k. So I've taken exactly k things, and I need to max this with 0 because I don't want negative infinity in there, because that's just part of the problem. If you can't take exactly k things, then you just return 0. Right, so that's my naive n squared. I want to see how fast this runs. I think that would be interesting. Let's see if it at least passes the samples, though. It doesn't even pass samples. And it's overcounting. Oh, I see why. Messed up my DP. What I want to do is I want to say that I'm not taking anything using this subtree. And then if it's better to take something in the subtree or take myself. That's my DP. So now this should pass samples. Or not. Allocate that much to DP. Maybe I'll do this build out a little differently. I'm gonna do a different style DP. Call this K1. I like my build out style DPs. So break out early in that case. Oh, yeah, I don't want to update this. I have to do this DP backwards. That's why. Right. I'll run it like that. So you might be wondering what I'm doing here. Basically, what I'm doing is I'm just finding the maximum K2 value that isn't negative infinity. And I'm just going to run through that backwards. I actually want the min of that and K minus K1. But I can get rid of that break. Okay, so dp of k, and then dp of k1 plus dp2 of k2. And so this should be correct. Yeah, so at least it's working now for that. But let's see how slow this thing is. Actually, I'm buffering my output, so let's not buffer my output. We can see absolutely how slow this thing is running per case. I think it'll freeze. It gets a lot of small cases fairly quickly, but then it's not nearly as fast as the other solution. The other solution ran this quickly, and then it gets out to these cases, it's just going to be super slow. Because it's roughly n times k squared. Oh, I guess it ran fast enough. Let's see if it's right. That'll be fun. Maybe pop over, open another terminal. Yeah, so that gets it right. I wonder if that's fast enough, though. It could have some nice amortized runtime. It's definitely slower than the n squared DP. Okay, so I did get a question in live chat. It says, just wondering, where did you learn all these techniques? So basically, I trained with the UCF team when I was an undergrad and master's student. And that's where I basically picked up all of this stuff because we have a culture where we just learn from each other. So I picked up a lot of these techniques, and I've been coaching the team like this for a while over here. So A lot of these techniques are just things that I talk about with students that want to train. Yeah, I don't know where I learned them. I take good notes though. I'd say I write down each of these techniques and I give them names and stuff, so I remember what they are. Because I think a lot of competitive programming, we have things like Dijkstra's or we have things like dynamic programming. They're all really well known, but these small little tricks like this, they tend to not. You tend to not think about them. So yeah, I tend to write these down, and I learned most of these tricks by solving problems or figuring things out on my own, or reading other people's code. So that's where I'd say I learned a lot of this. Okay, so I think you can get this down to one for loop though, because right now that this runs with 2 for loops and it's a little bit slow. So let's see if we can figure out how this works. Okay, so we need to take advantage of something here because I don't think there's anything we can do when we look at this DP table like this and see that it's improving. There doesn't seem to be a way to get this DP loop around unless we take advantage of a property. So one thing I want to point out to most of you, so I'll just print this out. I think this will be surprising to some of you. Maybe not if you've already seen it. I'm just going to print out the DP table at every single state. I think this is what's going to help me. Okay, what you should notice about this is this function is increasing as I'm going up in K until it gets to something that's not possible. So you see how it's 0, 1, 2, 3, 0, 1, 2, or it's non-decreasing. So you can have like 0, 3, 3, or 0, 2, 4, 5, or 0, 20, 18, something like that. I think that's what we need to take advantage of, is the fact that this is increasing function in our DP table if we want to cut off that innermost loop. Because if we knew what K was, so I wrote my DP in kind of a strange way. I knew what K was, what my optimal K value was for this DP, or what K value I'm currently looking for. I end up wanting to pair the max of one with the max of another in terms of what I can take. So let's see if I can deal with that. So if we try a split point, yeah, so I do want to take my largest jump, it seems. Huh. I think I want to take my largest jump until it stops being useful. Okay. And then maybe I'll wrap this up and explain how I want to do that to you. But here's the rough idea. What I'll do is I'll call this max. I'll just call this K2. It should work. I'll get rid of that. Here's what I'm going to do. I always want to allocate at least something to the other table. That's what I'm doing here. So basically, if taking a size K2 jump doesn't increase my answer anymore. Maybe I don't want to do that. I definitely want to take advantage. Let's go pen and paper, see if we can figure this out. So basically what we have here is I know I have an array that is going to be increasing or non-decreasing. And this is my DP table so far at this current level. Right, and then I have a bunch of negative infinities in my table up to a certain point. And what I like to do is I end up getting a new DP table that I want to, it's almost like a convolution if you think fast Fourier transform, if you know what that is. If you don't, that's okay. But I have another table state that's basically saying if I take k things in the subtree, I have this increasing function that can get me some reward. Maybe I'll take 8, 9, and then 10. And what I'd like to do is I'd like to just update this and n squared. I like to take a certain amount of this table, then combine it with this table efficiently, and not in k squared runtime. But they're both non-decreasing, which is nice. So there might be some threshold that I can end up taking. Huh. But I'm not quite sure how to do it. All right. So I don't think I have any good ideas on this. This is something I'll be thinking about, how to bring this down to K. And so if you end up finding out how to do it, let me know in the comments, because I think this is a pretty common trick. Maybe I'll talk about it some next week. But this is, you see this much more than the skipping list technique. But I feel like the skipping list technique can lead to very easy to code solutions sometimes. You saw how the other solution was much less complicated than this code here. So something to keep in mind for future weeks. Little bit of housekeeping stuff for the next week's episode. We'll be back to our usual time next week, Friday at 9 p.m. So you can tune in at my usual time. And not sure what I'm going to cover yet. I've got a few ideas lying around that I think could be really fun to talk about. But hopefully you've enjoyed this one. I think this technique is maybe not so discussed as often, especially the first technique, the one about skipping over subtrees. So I think it was interesting, or you can let me know in the comments if you think it was interesting. But I'll see you guys all next week on Algorithms Live. And yeah, try to figure this one out and try coding the knapsack problem, the other one that I posted in the blog. I think that one's pretty good too. It uses the same kind of ideas. All right, see you guys next week.